Today we are going to discuss about the current conduction in MOSFET. So we have to continue it with the new topic, that is we are using here that the effect of MOS system under external bias. So assuming that the substrate voltage is set at VB means bulk or the base, or we can say the substrate voltage is 0, and let the gate voltage be controlling parameter, because that we will give some voltage to the gate, then definitely it will affect or reflect to the MOS structure. So that's why we said that with the help of the external voltage phenomena, how this MOS is basically working. Okay, so depending on the polarity and the magnitude of VG, gate voltage, three different operating regions can be observed for the MOS system. What are those? First we have the accumulation, and then we have a depletion, and we have an inversion layer. Okay, so one by one we will discuss about it. So MOS gate structure is basically first electrode, that is gates, consisting of a low resistivity material such as highly doped polycrystalline silicon, aluminum or tungsten we can use here. Okay, so second electrode, substrate of the body, it can be a N or P type semiconductor basically, and the dielectric we are using here is silicon dioxide, because the silicon, when comes under the effect of the pressure of the oxide, so it becomes silicon dioxide, so which will work as a dielectric. So stable high quality electrical insulator between the gate and substrate. Okay, here we can see from the diagram that at the bottom layer where exactly we are connecting this base of the polysilicon with the ground, so that it can become 0. So p-type silicon substrate of the body we are using here. Then after we have a white color line, basically oxide layer, then we have a metal. Okay, and VG basically belongs to the gate voltage, where exactly we have to apply some voltage here, so that we can read out or the study the phenomena or the effect of this gate voltage onto the gate of the MOS structure basically, or TOX basically the oxide thickness. So gate and substrate condition for the different biased. So first condition basically belongs to when the VG is much less than VTN. Okay, so gate voltage is much less than VTN, means the threshold voltage of the N. Okay, so at upper layer we have a minus, and at a below level we have a plus. Plus is basically using because the silicon we have taken here is a p type, so that's why the p type is silicon basically having a carrier concentration of the plus. Okay, so this is accumulation condition. Accumulation condition is basically when there is a small charge is given, because the threshold voltage is much higher than the gate voltage, and that's why we have taken the condition which is much less than the threshold voltage. Then the another reason we have the depletion, when there is a slightly equivalent, when there is slightly equivalent of the gate voltage is less than, not much less than, it's less than to threshold voltage. So we can say that at upper level where exactly that we have a carrier concentration in the negative sense, but right now because of the depletion that we are trying to change this phenomena, and we are getting the value of positive here. And at a below level where exactly the region is being formed, so here the carrier concentration is in the negative form, but the p-type silicon we are using here, concentration or the hole's accumulation layer is basically the plus. Okay, and the width of the depletion layer is created here, which is having the carrier concentration or the accumulation in the negative sense. And then the last region is the inversion region, where exactly that we have the value of the gate voltage is greater than threshold voltage, and that phenomena is basically known as the inversion layer, where we have a depletion layer, electron inversion layer also created here, but the three conditions we have to discuss about it. Okay, so accumulation: if a negative voltage which is applied to the gate electrodes, the holes in the p type substrate are attracted to the semiconductor oxide interface. The majority of carrier concentration near the surface becomes larger than the equilibrium hole concentration in the substrate. Hence, this condition is called the carrier accumulation on the surface. Okay, and note that in this case the oxide electric field is directed towards the gate electrode, as we have shown in the diagram. The negative surface potential also causes the energy band to bend upward near the surface, while the hole density near the surface increase as a result of the applied negative gate bias. Okay, the electron, which is the minority carrier, okay, concentration decrease as the negatively charged electrons are pushed deeper into the substrate in this condition. Okay, so the MOS system under external bias, and the condition is accumulation. Okay, when the VG is nearly zero because the threshold voltage is much greater than gate terminal voltage. Okay, so in this condition we basically having the EOX, means the energy of the oxide layer, and then we have a hole accumulated on the surface of the oxide layer, and we are using the p-type substrate or p-type silicon substrate here, and putting the VV, which is substrate bias voltage, is 0. Okay, so here we can see that we have a metal oxide and semiconductor, but the phenomena we have to understand in the metal and semiconductor only. Oxide layer we have to neglect in this case. So here, as I told you, because of the negative voltage applying that we are at the gate, so the energy is shifting upward. Okay, so according to the diagram we have shown here. Okay, the cross-sectional view and the energy band diagram of the MOS structure operating in accumulation region basically. Okay, so MOS system under external bias, when we talk about the depletion layer, okay, a small positive gate voltage which is applied to the gate electrode, means the threshold voltage is not much less than, but it is a positive gate bias voltage is applied to the gate of the metal, okay, or the MOS. Since the substrate bias is 0, as VB is equal to 0, the oxide electric field will be directed towards the substrate in this case, because we applied the positive voltage here. Okay, the positive surface potential causes the energy band downward near the surface. Now in this case, that as we are applying a small positive gate bias voltage here, so the energy band is too, or the forcefully to be bent downward near the surface, but in the when we are applying a negative bias voltage to the gate, so it is shifted upward. Okay, so the majority carrier, that is the holes in the substrate, will be repelled back into the substrate as a result of the positive gate bias. Okay, and these holes will leave negatively charged fixed acceptor ion behind. They will leave it. They are not bother about it, that which kind of the acceptor we are leaving behind it. Thus a depletion region is created near the surface. Okay, note that under this bias condition, the region near the semiconductor oxide interface is nearly devoid of all mobile carriers. Okay, so here, according to the diagram, when we are applying a small positive voltage here, that is Vg is greater than 0, so what exactly to be happened here, this oxide layer or the accumulation of the charge carrier which was near to the surface is going to be shifted towards the p-type substrate, and the diagram, energy band diagram, is showing the shifting to the Si substrate. Okay, movement. Then the cross-sectional view and the energy band diagram of the MOS structure operating in the depletion under the small gate bias. So depth of depletion region and depletion region charge density. How we can get the mobile hole charge in a thin horizontal layer parallel to the surface is basically dq is equal to minus q into na dot dx, and the charge in the surface potential requires to displace the charge sheet, that is dq, by a distance x which has to be traveled here away from the surface, can be found by using a Poisson's equation, which is denoted by d phi s is equal to minus x dot dq upon Poisson's equation d phi s is equal to minus x dot dq upon epsilon si is equal to q into na dot x upon epsilon si dx. Okay, you can search it out. Integration we have to do it from the both side and we'll get a value of xd, that is a depth of the depletion region here. So having a value of, according to equation number 11, and then the depletion region charge density, which consisting solely of fixed acceptor ion in the region, is given by equation number 12. Okay, so now the third reason we have when we are applying the more positive gate voltage to the gate, that is known as the inversion layer. So if the positive gate bias is further increases, that we have a value of which is much greater than 0. So as a result of the increasing surface potential, the downward banding of the energy band will increase as well, because of the slightly increase the value of the gate voltage, the energy band is shifting towards the substrate. But as we are increasing further, definitely downward banding of the energy band will increase as well. Eventually the mid gap energy level, that is denoted by ei, becomes smaller than the Fermi level, efp, so only on the surface, which means that the substrate semiconductor in the region becomes n type. Okay, within this thin layer the electron density is larger than the majority holes density, since the positive gate potential attracts additionally minority carriers, that is electrons, from the bulk substrate to surface, and the n-type region created here, which is near to the surface by the positive gate bias, is called the inversion layer, and this condition is called the surface inversion. Okay, so it will be seen that the thin inversion layer on the surface with a large mobile electrons concentration can be utilized for conducting current between two terminals of the MOS. Okay, so here we can see the MOS system under an external bias, which is an inversion layer. The surface is said to be inverted when the density of the mobile electrons on the surface becomes equal to the density of the holes in the bulk, that is a p-type substrate. This condition requires that the surface potential has the same magnitude but the reverse polarity as the bulk of Fermi level, that is phi f. Once the surface is inverted, any further increase in the gate voltage leads to an increase of the mobile electrons concentration on the surface, but not to an increase of the depletion layer depth. Okay, so here when again we are increasing the gate voltage over here, that definitely it can increase the mobility or the mobile electrons concentration on the surface, but the depletion layer or the depth has been created would be same as it is. Okay, as it once it has been created. Okay, thus the depletion region depth achieved at the onset of the surface inversion is also equal to the maximum depletion depth, that is chi xdm, or we can say not a chi but xdm basically, which remains constant for a higher gate voltage. So using the inversion condition, that is phi s is equal to minus phi f, the maximum depletion region depth of the onset of the surface inversion can be found from the equation number 11. Okay, we can see here xd. Okay, so xdm is equal to this. Okay, so the creation of conducting surface inversion layer through externally applied gate bias is an essential phenomena of current conduction in the MOS. So here the pictorial representation basically represent or depict the inversion region when the gate voltage is much greater than. So what exactly to be happened here? The electron attract to the surface. Okay, and p-type silicon semiconductor, the carrier concentration change here. Okay, and we have created the depletion layer. So here, because that we are increasing again and again the gate voltage, so definitely the carrier concentration of the mobile carrier concentration can be increased, but the depletion depth would be same or the as it is. So here we can say that it has been crossed the EFP, or we can see that the bending of this energy band towards the surface is more. Okay, more and more. The cross sectional view and the energy band diagram of the MOS structure is surface inversion under large gate bias voltage. Okay, so thank you so much, and this is all about the three phenomena. We have accumulation, and we have accumulation region, we have depletion region, and we have inversion region here. Okay, so one by one we have discussed with you. Thank you so much.